Greeting to all. Today we will continue with the stress waves. So, stress wave, what is a stress wave? A stress wave is basically a propagation. It is a propagating disturbance in a solid medium caused by a sudden application of force. Like in case of impact or blast, as we have seen earlier, the forces are applied with a very high magnitude over a very short period of time. Okay. So, in this case the stress wave propagates through the medium. So, the blast and impact, okay, it qualifies, this is the impact event, and in this case, as you have seen, this is a blast event. Okay. So, in both the cases the time instances are very short with a very high magnitude of pressure or force applied to it. Okay. So, this two events qualifies as a event in which a sudden application of force is applied over a very short period of time, and hence the stress wave is transmitted through the media. Okay. The induction of the stress wave leads to a change in the stress profile, it leads to a change in the strain profile, and the displacement also changes as the stress wave moves through the material. Stress wave. The formal definition we introduce it like this. A stress wave is a form of acoustic wave that travels at a finite velocity through a solid material. It is generated whenever a sudden force, like in case of blast or in case of impact, is applied, causing a temporary disequilibrium. An acoustic wave is defined as a type of wave that involves the propagation of vibration through a material media. Okay. So, we are dealing with the material medium propagation. Continuing ahead, stress wave propagation in structure. Okay. So, there are few quantification for this. So, unaware area, distance region yet to experience the load. Okay. So, we will start from the bottom. Okay. So, we will start at the load application point, the initial point of impact or explosion. Okay. This is where the event has initiated. Okay. The impact event or the blast event, okay, has initiated. Okay. So, once the propagation continues, okay, so the region immediately affected by the load has a very high stress concentration or a very high strain concentration. Okay. So, then the stress wave propagates further. So, it is a carrier of load information throughout the structure. So, now our stress wave is propagating through the structure, okay, and in the distant areas. Okay. Since this event has occurred here, okay, but there are regions, okay, they are distance from the propagation point which are yet to experience the effect of the stress waves. Okay. So, when a structure is subjected to a rapidly changing load such as impact or explosion, part of the structure close to the point of application of the load can be highly stressed. Okay. So, this portion is highly stressed, while a more distant area, so, okay, this area is still aware of any loading having occurred. Okay. So, this area, okay, which is at the vicinity of the application of the load, this becomes highly stressed. Okay. And the other end, okay, if you look into a bar, okay, which is hit by a impactor. Okay. So, in this region, okay, the concentration of the stress may be very high, okay, and the end region it might have not seen the arrival of the wave. Okay. The message that loading has occurred is carried from point of application to other part of the structure by stress wave. Okay. So, the stress wave, okay, the stress waves carries the information, okay, that the structure has been hit and the waves needs to be propagated like this. Okay. So, this is how the stress wave is quantified. So, now we are looking into one dimensional elastic stress wave propagation. The simplest example might be a bar which is hit by an impactor. Okay. So, we are considering a rapidly changing force being applied actually to the end of a thin homogeneous straight bar. Okay. The bar is thin, it means that the cross sectional dimension is less as compared to the longitudinal direction. The D and B are very less as compared to the length. Okay. Homogeneous, okay, the constituents of the material is same throughout the media. Okay. So, it is being hit by a impactor. Okay. The simplest case is that cantilever bar hit by a hammer. Okay. Now, we are looking into the stress wave, how the stress wave propagates in a bar. Okay. The force is applied to the end. Okay. This ends. Okay. This ends sees the application of the force. Near to this end, the initial particle displacement occurs. Here, the initial particle displacement will occur. Then this particle is going to interact with the next particle and it will cause the disturbance in the next particle, and this will again propagate forward and cause the disturbance in the next particle, and so on and so forth. The stress will be propagating through the entire media. Okay. So, this is how the stress will propagation occurs. Okay. First, the force is applied to a particular end, the initial particle is disturbed, this is the application of the force and the initial particle is disturbed and then interacts with the next particle and disturbance of the next particle occurs, and then the disturbed particle again interacts with the next one and the next one and the next ones, and so on and so forth, and hence the stress wave propagation through the media occurs. Okay. So, this is constituted by high speed travel. Okay. So, interestingly, for a one dimensional object, the stress wave velocity, okay, c, okay, can be expressed in terms of root over E over rho. Okay. So, this is a very interesting equation. Okay. We will talk about it when we are doing the finite element simulation also, but for now on, let us keep in mind that the stress wave velocity is in this form, root over E, that is the Young's modulus, and rho, that is the density of the material. This is the Young's modulus of the material. Okay, and this is the density of the material. Okay. So, this equation, okay, this has many applications in the field of non-destructive testing, in the field of finite element method, and as we go through the course, we will be discussing when we encounter this equation in the other fields. So, initially the force is applied to the particles at the very end of the bar, that is what we said, that in this bar at the end the impact occurs. This displaced by a tiny amount, the initial disturbances occur. This means that the initial disturbance is occurring and hence it will disturb the next particle, disturbance of the next particle occurs, and then the stress wave propagates along the bar. The propagation of the stress wave is in the bar. Okay. So, this is a very simple case in which the propagation of the stress, okay, due to an impact event is being shown. Okay. Moving ahead. So, now we will try to calculate some quantities. Okay. So, we will try to calculate the stress wave velocity and the one dimensional stress wave equations. Okay. So, we have a bar, okay, and in the bar we are taking a differential element dx. Okay. We have cut out this differential element AB. Okay. So, in a bar, an element of the bar within cross sectional area, initial cross sectional area A naught, the naught represents the initial, and length dx, okay, a very small piece, okay, having a finite length dx at a distance x from the. So, we are considering the distance x from the point of application of the loading. Okay. So, the impact event is occurring at this end. Okay. So, face A is displaced by u. Okay. So, this face, okay, let us say that the displacement occur in this face is u. So, now you can see the face A, okay, this face A, now it is here. Okay. So, this face is displaced by a displacement u. Okay. So, axial strain is, okay, change in length over the initial length. So, axial strain is dou u over dou x. Okay. So, we are considering tensile strain as positive. Okay. So, the new length of the element is given by this equation. Okay. So, axial strain in the element becomes the new length over the length, total length. Okay. So, this becomes the axial strain. Okay. And the compressive stress, we are just equating this strain. Okay. We know the relationship that stress is directly proportional to the strain. So, we are using this relationship to calculate our compressive stress in the element. Okay. So, moving ahead. Okay. So, the net axial force on face A prime B prime. Okay. So, the net axial force on this face is acting on the face B minus acting on A. So, the net force is the force acting on face B minus face A. Okay. So, the force acting on face A on face B and the force acting on face A. Okay. So, we can calculate the net force acting on the elemental area AB, A prime B prime. Okay. So, the mass of the element is nothing but density into the volume, and volume is nothing but my cross sectional area times the length. Okay. So, this is how we are getting the mass of the element. So, the acceleration is given by this expression. So, by the Newton's second law of motion, okay, we can relate the forces with the acceleration. Okay. So, substituting the relationship, we get the relationship between the forces and the acceleration. Okay. So, this is a well known type of equation, and this is called a wave equation. Okay. And through this equation we can be shown that this relationship occurs. Okay. So, this equation will be used in order to describe the propagation of the stress wave through the solid media, okay, when considering a bar. Okay. So, basically what it is doing is that using the second law of motion, this is relating the forces, okay, with the acceleration. Okay. Okay. So, formally in space time, okay, in one dimensional space and time, we are representing the equation. U is the displacement of a material point at a given position and at a given time. C is the wave speed of the material. Okay. So, this expression is giving the spatial curvature of the displacement, okay, that is the strain gradient, and this equation is giving the acceleration. Okay. So, some well known values of the wave speed. So, in steel, okay, we are normally considering a Young modulus of 200 and density of 7850. So, we get a wave speed of around 5000 meter per second. Aluminium, similarly it behaves in the same way. So, the wave speed is almost similar. Glass slightly higher, concrete is the lowest. Okay. So, as you see, once we are getting from a dense media to a less dense media, the wave speed is decreasing. Okay. So, if we have a very dense media, the wave speed will be higher, and in a less dense media, the wave speed will be lesser. Okay. Moving ahead. So, relationship between particle velocity and stress. Okay. So, although a stress wave may move through a body at a tremendous velocity, as we have seen earlier, okay, the velocity is around 5000 meter per second. Okay. So, this is a very high velocity. So, though the velocity might be very high, the actual velocity imparted to the particle in the body and the stress wave is typically very small. Okay. So, a direct correlation can be obtained between the velocity of the displaced particle at a stress pulse passes and the magnitude of the stress. So, we are using our old relationships. Okay. So, stress is related to the strain and modulus of elasticity is related to the stress wave velocity. So, substituting we get this equation. So, the stress wave velocity is the speed at which the wave passes along the bar. Okay. So, therefore, this is directly relating my stress to the modulus of elasticity and density. Okay. So, now we get the relationship between the stress and the particle velocity. Okay. So, this is the particle velocity and this is the stress in the material. Okay. So, using this equation we can get the direct equation between the stress and the particle velocity. Okay. So, in this case we see that for a given case C and rho will be constant. Okay. So, for solids at elastic strength level, the value of C and rho will be roughly constant. So, there is a linear relationship between the magnitude of the axial stress and the velocity imparted to the particles in the velocity. So, the axial stress rho is directly proportional and there is a linear relationship between the velocity imparted to the particle in the body at the stress wave passes over them. Okay. So, this is the expression. So, equation. So, this has some resemblance to the Ohm's law with the stress and particle velocity corresponding to the voltage and current in a circuit. Okay. So, in this analogy the product rho C corresponds to the resistance. Okay. So, this is stress, okay, and if this is velocity, so this quantity rho C can be written as a resistance, okay, and this is also called as the acoustic impedance of the body through which the stress wave is passing, okay. So, we are introducing a term called acoustic impedance. This is nothing but a form of resistance, okay, when the velocity, when the stress wave passes through a media. So, the relationship between the stress and the particle wave velocity is given like this, and the constant is called the acoustic impedance, which is a form of resistance. Okay. So, this was the stress wave behavior in the body. So, now we are looking at the stress wave behavior at the boundaries. What happens when the stress wave reaches the boundaries? Okay. So, when the stress waves encounter boundaries, okay, for example, material interface or free surfaces, their behavior is governed by the acoustic impedance. Okay. So, now we will be looking more into the acoustic impedance. Okay. So, remember, acoustic impedance is nothing but a form of resistance, okay, where rho is the material density and c is the stress wave velocity. Okay. So, this impedance affects wave behavior at material boundaries. Okay. So, at the boundaries what happens? Okay. So, there is a impedance mismatch. Okay. If there are two different materials, okay, their C and rho will be different. Okay. So, straight away there is a impedance mismatch. Okay. So, then in one of the material there might be a minimal wave reflection, and in the other one there might be a significant wave reflection. Okay. In one there might be high wave transmission depending upon the value of C and rho, and in the other one there can be low wave transmission. Okay. So, elastic reflection. So, if elastic reflection is occurring, then the elastic reflection preserves wave energy and momentum. In elastic reflection, the elastic reflection reduces wave energy and momentum. Okay. So, reflection of one dimensional stress wave at boundaries. Okay. We will now see what happens at the boundaries when the reflection occurs. So, the behavior of stress wave in a bar which strikes a discontinuity. Okay. For example, we are seeing, if we encounter a case like this, okay, where there is a discontinuity. This is the point of discontinuity where the cross section is changing, A1, A2, the modulus is changing, it is made up of two different materials, again density, two different materials, and the wave speed will, since this is dependent upon the E and rho value, automatically the wave speed is different. Okay. So, we are considering a bar which at some point changes in point cross sectional area and materials. Okay. So, both the cross sectional area and the material are changing. So, okay. So, we will see how the stress wave is behaving at a discontinuity. So, we will assume that when the incident stress wave is split into two parts when it hits the discontinuity. Okay. So, this is our assumption, the incident stress wave. Okay. This is the incident stress wave and it is split into two parts. Okay. At the moment it hits the discontinuity. A reflected wave which passes back into the first part of the bar, and a transmitted wave which propagates into the second part. Okay. So, there will be two parts, okay, one part that will go through and the other part that will be reflected of the initial wave. Okay. If this is the initial wave, then there will be two parts, there will be a reflection parts, which there will be a reflected part and there will be a transmitted part. Okay. Okay. So, for the equilibrium of force, okay, we know that the force equilibrium has to be maintained. Okay. So, the incident part and the reflected part, okay, transmitted part and the reflected part. Okay. So, the transmitted part, okay, has to be sum total of the incident one and the reflected one. Okay. So, the transmitted one should be a sum total of the incident and the reflected one. Okay. So, the transmitted one is related by this equation, and for the compatibility of the particle velocities to occur, the incident one and the reflected one are related by this transmitted one. Okay. So, we get two relationships, one from the force equilibrium and one from the compatibility part. Okay. So, we know this relationship, okay, the relationship between the stress and the particle velocity, okay, that we have seen in the earlier section, and the reflected and incident waves are on the same side of the discontinuity. Okay. the incident and the reflected wave are on the same side of the discontinuity and transmitted one is on the other side. Okay. So, the incident wave and the reflected wave are on the same side of the discontinuity and have the same density and the same speed values. So, we can change the relationship and change it back into the stress equation. So, now we are putting this back into equation 1. Okay. So, we had this equation. Okay. Now, we related the particle wave velocity with the stress. Okay. And since the reflected and incident wave, okay, they are both traveling on the same material. So, we can substitute their relationship. Okay. So, combining this with the first equation, we got a relationship between the incident stress and the transmitted stress. Okay. And again substituting the stress value back from the particle velocities, we get a very clean relationship which relates the transmitted stress, okay, with the incident stress. Okay. Okay. So, after doing some simplifications, okay, the final form we can get using this, okay, where the transmitted stress and the incident stress are expressed in terms of the impedance. Okay. And as we have seen, this was our equation for the impedance, okay, I equals to rho c. For the corresponding material, we will just put the I equals to rho c. Okay. So, rho is constant, c is more or less constant. Okay. So, we are relating the transmitted stress and the we are relating the transmitted stress, okay, here. So, incident stress, okay, that was coming from the first body, okay, which got split up into two parts. So, there was incident stress, okay, it got split up into two parts, transmitted and reflected. Okay. So, now we are able to relate the incident stress with the transmitted stress. Okay. So, we can calculate if the value of the incident stress is this much, then the value of the transmitted stress will be this much. Okay. So, now again we are trying to get a relationship. So, this covers the relationship between the incident and the transmitted wave. Now, we will try to get a relationship with the reflected wave also. Okay. How much it is being absorbed back into the initial system. Okay. So, for the reflected stress, okay, we got this relationship with the incident wave. Okay. So, now using these two relationship, okay, we can relate the incident stress, okay, back to our transmitted stress and the reflected stress. Okay. So, reflection of one-dimensional stress wave at boundaries. Okay. So, for the free surface, what happens when the stress wave hits a free surface. Okay. So, the simplest case of discontinuity is a free surface. Okay. This is the simplest case of discontinuity. In discontinuity, what we were saying, so what might happen? The cross sectional area will change, the material can change. Okay. The simplest form is that there is nothing on this side. Okay. So, we will try to look into what happens at the free surface. So, in this case, the acoustic impedance of the material body beyond the discontinuity, okay, from equation B and C we get that the transmitted part will be 0 and the reflected part will be the negative of the incident wave. Okay. There is no transmission, okay, simply, and the whatever was being applied, that is being reflected back in the body. Okay. So, this becomes the simplest case of the discontinuity. So, the reflected wave is of equal magnitude, okay, because nothing has been transmitted. So, everything comes back into the original body, and since the incident wave was going in this direction, the reflected wave will go in the other direction. So, the reflected wave is of equal magnitude and opposite side to the stress wave, as we can see here, and this means that a compressive wave, incident wave, will be reflected from a free boundary as a tensile wave. So, if this was going as a compressive wave, this will be reflected as a tensile wave. Okay. If the incident wave is compressive, then as it passes from left to right, okay, particle wave will be pushed to the right. Okay. If it is moving from left to right, particles will be pushed to the right side, okay, as you can see there. And when it is reflected as a tensile wave traveling from right to left, okay, in this direction, it will pull the particle towards the right. Okay. So, this is how the stress wave behaves, okay, in a discontinuity, and where the discontinuity is nothing but just a free surface. Okay. So, this we are deriving from this equation. Okay. Okay. So, a rigid surface. Okay. So, in the case of a rigid surface, the acoustic impedance of the rigid bodies is infinity. Okay. I equals to rho c. So, this resistance is infinite. Okay. The transmitted stress wave is meaningless. Okay. Since by a definition a rigid body has infinite Young's modulus, and from equation C the reflected stress is nothing but the incident stress. Okay. So, an incident wave is on the boundary of rigid body produces a reflected wave of equal magnitude and sign. Okay. So, geometric discontinuities, in this case the material stays the same. Okay. In the previous case we saw that the cross section was changing and the material was also changing. So, we are looking into a case where only the cross section is changing, okay, the material remains the same. So, we can simplify the equations, both the given equations, and find out a relationship between the transmitted and the incident wave and the reflected and the incident wave. Okay. The terms in the brackets are known as transmission and reflection coefficient. In this case, this term is known as the transmission coefficient and this term is known as the reflection coefficient, because it simply gives us a relationship between the incident wave and the transmitted wave, and here it gives a relationship between the incident wave and the reflected wave. So, these are just the coefficients, and the sign and the magnitude of the transmitted and reflected waves are determined solely by the ratio of the bar area on the either side of the discontinuity. Okay. The sign will be determined by this bar area on both sides of the discontinuity. Material discontinuity. So, here we are looking into a case where the cross section remains the same. So, what we are trying to do, basically what we are trying to do here is that we had this initial equation. Okay. So, in this equation we saw that the material and the cross section was different in both the cases, and we derived a relationship between the incident wave and the reflected wave, incident wave and the transmitted wave. Okay. And this term in the brackets, okay, this was a function of both the material properties and the cross sectional area, both the material properties and the cross sectional area. Now, what we are trying to do is that we are trying to see one by one. In one case we are keeping the material constant and see what happens with the relationship, and in the other case we are keeping the cross section constant and changing the material and see what happens. Okay. So, in the first case where we have kept the materials constant, okay, the material stays the same, only the cross section changes, then the term in the brackets are known as the transmission coefficient and the reflection coefficient, and the sign and the magnitude will only depend upon the corresponding cross sectional areas. Okay. In the second case we are keeping the cross section same, but we are changing the material. Okay. So, again we will try to see what happens here. Okay. Okay. So, this again we can call it as the transmission coefficient and the reflectant coefficients, where the sign and the magnitude will depend upon the density and the stress velocity, okay, between the two materials. Okay. So, now we are trying to describe one very simple experiment, okay. By using that we can determine the one dimensional stress waves. Okay. So, this is called the split Hopkinson pressure bar. Okay. So, this is nothing but, imagine that you are playing the game of snooker. Okay. So, what happens? You have a finite particle, okay, in the form of a ball, okay, and you hit with a velocity by your striker. Okay. The ball will try to move. Okay. So, in this experiment what we do is that we make it guided. Okay. So, this hitting of the particle with a striker is in a guided form and the velocity is very high. Okay. And then we will try to see what happens to this bar. Okay. So, this is the incident bar, the striking bar that we were talking about, and this is the specimen. Okay. So, in the snooker what happens is that there is only one bar, okay. It hits the material. Okay. So, here what we are doing is that we are keeping one more bar. Okay. So, this is just holding this in position. Okay. And then we will try to measure the strain profile of the specimen. Okay. So, this is a very simple experiment that is used to determine the behavior of the material during a very highly dynamic event. Okay. So, this equipment consists of two long thin cylindrical metals, usually steel. Normally steel is used, but sometimes aluminum or titanium things be used. Okay. So, these are nothing but the two strikers that we were describing here, and in between there is a very thin sample of specimen. Okay. Whatever sample you want to test. Okay. It can be concrete, it can be any metals, okay. It can be any ceramic. Okay. So, using this experiment, what we do is that we measure the strain profile, and then the strain profile is related back to the stress profile, and we can get the material properties. Okay. So, between these two bars, okay, the material is being sandwiched. Okay. So, now we will try to analyze stress waves in material. Okay. So, what happens? The striker bar hits the incident wave, okay. The wave propagation occurs, the wave interacts with the specimen, reflection and transmission occurs. Okay. When this thing hits it, okay. So, there will be a part called reflection, and there will be a part getting transmitted. Okay. And since we know the materials of this properties, okay, we can calculate the quantities. Okay. So, there is a strain gauge out here. Okay. So, the strain gauge measures the incident, reflected and transmitted waves. Okay. We can get the entire signature of the incident, reflected and the transmitted wave, and the measured waves are used to calculate stress and strain within the specimen. Okay. So, this is the discontinuity, this is a discontinuity. Okay. So, we know the values going out from here. Okay. We are measuring the values out here, and using the relationship we can calculate the material properties from this simple experiment. Okay. So, this is split Hopkinson is widely used to characterize the materials. Okay. Any unknown given material we can characterize using the split Hopkinson test. Okay. So, split Hopkinson test. Okay. So, this is the theory that we described earlier. So, this is the theory described earlier has been implemented for this experiment. Okay. And different quantities are being calculated here. Okay. So, as you can see here there is an interface between the incident bar and our body. Okay. So, this is the incident surface, this is the reflected one, and this is the transmitted surface. Okay. So, we have the relationship, and using the relationship we can calculate the entire profile. Okay. So, if you go through these things, okay, we have the cross sectional area and the properties of the bars, and using back calculations and the measurements we can calculate the properties of the specimen. So, you can go through and devise your, you can take your own material, and using this material you can characterize and you can get the properties of the materials, okay, in a very high strain event. Okay. So, with that we conclude this lecture. Thank you.